Hello, my name is Yejoon Lee from ADAS Lab at Seoul National University. This talk was originally given at an internal seminar at the lab, but here we share with a broader audience. So if you have any questions or discussions, feel free to contact me. So this talk discusses about the KV efficient language models, and as a couple of examples, I'll introduce MLA, the multi-latent attention, and sliding window attention. So here are three takeaways from this talk. Number one, KV size explodes in naive transformers. And number two, recent language models adopt KV efficient transformer architecture starting from the training. And the number three is the question: how truly useful are inference time KV efficient solutions as these KV efficient transformer architectures are becoming the norm? So first, I'll talk about the background, the KV caching. So here, I'll assume you know the basics of transformer and attention. And in this picture, as you can see, this X is the hidden state, so the input to the transformer layer. And this X is projected to queries, keys, and values. And from these queries, keys, and values, the attention is performed. And well, by doing these and other operations like MLP, we could generate the first token. And if we were to then generate the second token, we could basically do the same, but only this time the sequence dimension is 2 instead of 1. And in this picture, the gray blocks represent the first token, while the purple blocks represent the second token. But this picture does not depict the exact process where the second token is generated, because during inference we only need to decode the next token, so the last input token. So this will correspond to the purple token. What this means is that we do not need a query for the first token, which is this gray query blocks. However, we still need the keys and values of the first token because the query of the second token needs to attend to the keys of the first token. And then also the value of the first token is used. But we do not have to calculate the keys and values of the first token because this was already calculated when generating the first token. So we could save the keys and values of the previous tokens and reuse them when generating the future tokens. And this is known as the KV caching. And well, basically every transformer language models use KV caching. Next, I also want to talk about the prefill. Prefill means calculating all the KVs of given input tokens. So if there are two input tokens, in order to generate the next token, we need the KV of these two tokens. And calculating the KV of these input tokens does not need to be done sequentially. It could just be done in parallel. So in matrix multiplication. And this is what's exactly done in transformer during training. And this is the prefill. So that's it for the KV caching. And now let's talk about why large KV is problematic. Before we talk about the problem, let's see the simple formula for calculating the KV cache size. And a little disclaimer here is that this formula works for the most standard transformer language models, but may not apply to heterogeneous language models. So the simple formula goes by the number of layers times KV dimension times 2 times size of KV data type times sequence length. So let's see the Llama's Rebellion model for an example. There are 28 layers in this model with KV dimension 1024, and the KV data type is brain float 16, so that corresponds to 2 bytes. And the sequence length S, of course, decides the exact KV cache size. And let's assume that S is 128K, which is, by the way, very, very large. And in this case, KV cache is 14.7 gigabyte. And you may think that this is not large, but what you have to remember is that this model is a small model. So this 3 billion model will account for 6 to 7 gigabyte for wait and activation. So the KV cache size is about twice as that, so it is not negligible. And this is a side note. And this model, Llama's Rebellion, and a lot of modern language models actually have reduced the KV size by using what's known as GQA, or grouped query attention. And this is illustrated as the KV dimension 1024 is much smaller than the model dimension, which is 3096. And in this talk, I'm not going deep in GQA, although GQA is very, very important. And that's mainly because GQA has already become the standard of language models, while this talk is focused on introducing more nascent KB efficient architectures. So why is large KV problematic? And for this, we will separate the two main phases of language model inference, which are prefill and decoding. So for prefill, large KB is problematic because then prefill takes a lot of time. And as we all know, the time complexity of attention or transformer is O(S) squared. So prefill can take a lot of time if S is large. And large KV is also a problem in decoding phase, because currently the decoding phase is bottlenecked by the KV transfer between HBM and on-chip memory. And this has led to the invention of flash attention. Or in some cases, KB may not fit into a single HBM, and this will force other techniques such as CPU or disk offloading. And obviously this would be much, much slower than just transferring KV between HBM and the chip. And as you've seen in the KV size formula, the KV size grows linearly with respect to the sequence length. And I think the biggest problem here is that S is just keep growing. And as prefill and decoding is both bottlenecked by S, this is a significant problem. And researchers already acknowledged this problem, and this led to various inference time KB efficient solution. And here I will only introduce a brief list. So for prefill, one solution would be doing a prefill via sparse attention. So this would be better than O(S) squared. And another solution is to save and reuse KV instead of calculating it every time. The examples include prefix caching and non-prefix caching, for example, cache blend. And there are KVs across the transformer layers. So you can think of a solution where KV is shared across the layers. And for decoding, flash attention is the prime example. And because the large KV size is the problem, many solutions try to compress the KV. So for instance, we could evict the KV of certain tokens, or we could low rank decompose the KV, or quantize the KV. And here I want to differentiate between the free lunch solutions and the others. And by free lunch solutions, I refer to those without performance degradation. In other words, these solutions result in the exact same computation. So the free lunch solutions here are prefix caching and flash attention. And well, there are a lot of solutions and works on inference time KV efficiency solutions. But the main question of this talk is, what if we train the language models to be KV efficient in the first place? And of course, there will be many works on this direction, but in this talk, only 2 examples are introduced: MLA and sliding window. And other examples would include chunked attention or other MLA-inspired variants. And these solutions still maintain the transformer architecture, so the attention, but more radical approach would basically overhaul the attention. And the prime example of this is these space models, such as Mamba. Let's begin with MLA. And MLA, the multi-latent attention, is from the DeepSeek team. MLA, the multi-latent attention, was first introduced in DeepSeek v2 and is adopted in most of the recent DeepSeek models, maybe all, and also adopted in a recent language models Kimi K2. And the key idea of MLA is simple. It low rank decomposes the KV. So let's see more of it. So this right figure is from the DeepSeek v3 paper, and it could be a lot at a first glance, so it would be good to follow these colored boxes. So the core idea of MLA is to cache the latent of KV, not the KV itself. So the latent of KV is denoted by CTKV here. So this dashed means that it is cached during inference. And here this subscript T means the token T. And you can also find the subscript I in this figure, and this represents the attention head I. So this 3 equations shows the down projection to latent, and then reconstructing KV from this latent. So HT is the input hidden state, which is down projected to the latent, CKV. And this CKV is up projected back to respectively key and value, which are the keys and values for the attention. And one notable characteristics of MLA is that it also compresses the queries. And it's basically the same. The HT is down projected to CQ, which is the query latent, and the CQ is up projected back to QC, which is the query. And if you think about it, this has really nothing to do with KV. It does not reduces KV size or do anything with it. And you could just think of it as another detail of MLA. And this implementation also actually helps reducing number of parameters. If you think about projecting input hidden state H into query Q, without latent, it requires d times dq parameters. And here d represents the dimension of hidden state, and dq represents the dimension of query. But if we use the latent, we only need r times d plus dq parameters. And if r is smaller than d and dq, this will be a lot smaller than the version not using latent. An important aspect of MLA is that reconstructing queries and keys and QKT can be fused. So let's look at the equations. Here CQ is the query latent and QC is constructed from this latent. And likewise, CKV is the KV latent and KC is the key. And what we want to do with these queries and keys is doing dot product. And if we plug in these equations into the dot product, you can see that the W, which projects the query latent, and another W, which projects the KV latent to the key, can be fused into a single operation. So in other words, the reconstructed queries and keys are never calculated. Only the attention values between queries and keys are. So this is definitely awesome, but there is a problem. And that is that this fusion is incompatible with positional embedding rope. And in this talk, I won't go in detail with rope, but what basically rope does is encoding a positional value for queries and keys. So after this query latent is up projected to query, the rope should be applied to obtain a true query, a positional embedding incorporated query. And the same is for key. And the problem is that if we do the rope, we cannot do the fusion. So let's look at the equations. The first equation shows the dot product between query at position t and key at position t. And the second equation represents the dot product between query at position t and key at position s. And because rope is token position dependent, this blue part and red part won't be the same because the rope operation will be different because of the difference in key token positions. As a result, a single fused weight cannot be derived. So how does MLA tackle this problem? MLA solves this by reserving queries and keys to care rope. This means that there are few selected queries and key dimensions where rope is applied. And this is implemented a little differently in query and key. So let's look at the equations. Here CQ is the query latent, and with up projection and then rope, it becomes the QR, the query where rope is applied. And it is similar for key. HT is the hidden state, which is projected and then roped, which results in the KR, the key where rope is applied. And as you can see in the figure, this KR is shared across the heads, while QR is different by head. QR can be different by head because the WQR, the up projection matrix, is different by head. And as you can see, this rope key can be cached and reused. By isolating the query and key dimensions where rope is applied, MLA can fuse the remaining dimensions, as we've seen in fuse slides before. So this blue part is basically where the calculations are fused. So for hidden states H and KV cache CKV, the latent KV cache CKV, all the calculations can be fused and go directly to Q.K. So only for the non-rope dimension, so to speak. And this single calculations fuses a total of 4 operations. And that is, first, this HT is down projected to correlatent, and then up projected to query. And this KV latent is up projected to key, and this up projected query and up projected key is dot producted, which is the final result. And of course, for the query and key dimensions where rope is applied, there's no fusion trick. We have to do all the calculations step by step. But as you can see in the MLA configurations, this non-rope dimension is much, much larger than rope dimension. So this very much accelerates the MLA process. So intuitively speaking, MLA splits the content dimensions from the location dimensions within query and key. So back to our main agenda. How does MLA reduce the KV cache size? The way to calculate the per layer per token KV cache size in MLA is KV latent dimension plus rope key dimension times S. So this KV latent is the CKV and the rope key is the KR. And in DeepSeek models, this is given by 512 and 64. So this results in the KV cache size of 576 times S. And compare that to canonical transformer. The KV cache size of canonical transformer is 2048 times S. Here 2048 is given by 1024 times 2, where 1024 is the KV dimension. And of course, this would vary by model to model, but 2048 is a pretty standard number for canonical transformer. So for comparison, MLA slashes KV cache size by about a quarter. So this is the details of MLA. And before we move on, let me summarize the core mechanism of MLA. The key motivation of MLA is to only cache the latent, not the KV itself. And the expressiveness of KV is handled by computation by reconstructing the key and value from the latent. And obviously, this would result in more computation overhead in return of saving the KV cache size. And this computation overhead can be vastly reduced by clever fusion. And this clever fusion is allowed by the effectiveness of partial rope, where we only apply the rope to the few dimensions of queries and keys. And this was it for MLA. And next is the sliding window attention, which is a popular simple workaround to reduce the KV cache size. And sliding window attention is really simple. Sliding window attention only attends to the fixed amount of pass tokens. So let's look at this picture. Left shows the global attention, which is basically the vanilla attention. So when the query token is E, it attends to itself E and also the 5 previous tokens. However, if we use the sliding window attention, we can set the fixed sliding window and only the tokens within the sliding window is attended. So in this figure, sliding window is set to 3. So even though the query token is E, it only attends to the past 2 tokens. So it does not attend to E, X, and A. Usually, the sliding window attention layers are used alongside with global attention layers. So they are interleaved within a single model. And this shows the result for Gemma 3 4 billion. And this dimension 2 represents the sequence length. And as you can see here, the layer 0 to 4 and also layer 6, the sequence length is 1024, while for the layer 5, the sequence length is 74,000. So this means that the layer 5 is a global attention layer, and perhaps the input length was 74,000. And the other layers shown here are the sliding window attention layer, and the attention and the window size is only 1024. And perhaps due to its simplicity, open weight language models often uses sliding window attention. So here are a few of the lists, including Gemma, Mistral models, Cohere models, Lemma 4, and EXA1. And these are the configurations of these models. So how they are interleaved and the size of the sliding window. So MLA and sliding window attention are only a few examples of KB efficient language models. And the main points I want to raise in this talk is that with the rise of KB efficient language models, how truly useful are inference time KB efficiency solutions. And this is a little side note, but I believe there may be a scale bias of research papers. And what I mean by the scale bias of research papers is that research papers primarily use smaller language models than large proprietary language models. And the inefficiency of KB may be more pronounced in smaller language models. And that is mainly because when we scale the language models, we do not scale the KB dimension. So let's look at a couple of examples. If you look at Qwen 3, the KB dimension of 4 billion model is 1024, which is the same for a 14 billion model. And somewhat surprisingly, this is slashed into half for 235 billion model. And this trend also is consistent within Llama 3, where the KB dimension is 1024 both for 8 billion and 70 billion model. So because KB dimension is not scaled, KB is scaled only via number of layers. And if the language model adopts mixture of experts, which is the vast majority of the case for really large language models, KB scaling becomes much smaller to that of model scaling because mixture of experts scale the MLP, not the attention. Therefore, inefficiency of KB could be more pronounced in research papers than in large proprietary language models. So in research papers, we might think, wow, KB cache is really large compared to model, but that may be less pronounced in large models, at least in a relative sense. So this was a little side note. And the next point is that will solutions designed for naive transformer hold for more efficient ones? And here is an illustrative example. Imagine there are language models under 10 billion parameters and the sequence length is 128K. For language models using naive transformer, such as Qwen 3 4 billion, the KB cache size is quite large as you can see here, about 19 gigabytes. Before Gemma 3 using sliding window attention, the KV size is 2.7 gigabytes, much smaller. And imagine there's this solution A, which reduces KV use by half with only 5% performance decrease. This is good, but if we fix this performance decrease budget by 5%, solution A will likely reduce KV use by less than half. And this is because the KV of Gemma 3 is, I would say, more compressed, starting from the training. And on top of this reduced compression ratio, the absolute size of KV is smaller in the first place. So even for the same compression ratio, the absolute amount of KV saved will be much smaller in KV efficient language models. So what is the point here? Research papers so far mainly experiment with naive language models, naive transformer using language models. However, a portion of their claimed gain may wash away within KV efficient language models. And this is the point. So, to summarize, free lunch solutions like flash attention and prefix caching are genius. Like, no one hates these free lunches. And free lunches will always have the power. However, a lot of KV efficiency solutions sacrifice performance for speedup. And this could be still fine, but the problem is that in general, training KV efficient language model in the first place will be better than post-hoc inference time solution. And as we can see from the DeepSeek's MLA or Elista models using sliding window attention, these KV efficient architectures are increasingly becoming the norm. So what are the takeaways? I think one obvious takeaway is that researchers should also consider how to apply inference time solutions to KV efficient language models, as they are increasingly becoming the norm. And somewhat more controversial one is that these inference time KV efficiency solutions may not be as useful as language models becomes more KB efficient in the first place. I know this is quite controversial, and I myself do not have really confidence in this statement, but I think this is a point we could think about. And I think the community is moving towards KV caching for KV efficient LMs slowly. During preparing this talk, I was quite surprised to know that the Hugging Face Transformers library is slightly buggy with interleave sliding window attention. And I believe this is a known issue with at least Gemma 3. And actually there is this pretty large scale refactoring going on. So this is a PR that is not marched yet, but this is a PR to refactor the KV cache implementation of transformers. So if you're interested, this PR is worth looking. And these days, VLM is a popular choice for LLM inference. And there's this recent paper from the VLM team from March 2025. And this paper, Jenga, introduces efficient memory management. So here memory, I think, includes the KV for serving LLM with heterogeneity. So here heterogeneity does not only mean KV efficient language models. As you can see in the figure, there are also multimodal LLMs, But this obviously includes the KV efficient language models. So I believe these changes will be more prominent in the coming days. And that was the end of my talk, and thank you for listening.